Okay, I want to mop up some stuff here from looking at our ethers, as well as go back and talk a little bit about oxidation of alcohols that I think was in previous readings, but I want to go back. I didn't put it on the exam, and I want to go back and take a look at that. So I'm probably going to be live lecturing at least through today and Wednesday, and maybe Friday as well, because the free radical halogenation is stuff that normally in the old book was done in the first semester. So that's where I want to go today. So first, I want to go back and talk a little bit about the oxidation of alcohols. So in our oxidation schemes, we have a primary alcohol can be oxidized, and a brackets with an O means it's sort of a generic oxidation. That can be oxidized to either an aldehyde, and then the aldehyde can be further oxidized up to the carboxylic acid. So for a primary alcohol, you can go to aldehyde, you can go to carboxylic acid. And then of course we've seen that for the reduction that we can reduce an aldehyde to a primary alcohol, and we can also reduce a carboxylic acid all the way down to the primary alcohol. So that's the scheme of oxidation reduction for a primary alcohol. For a secondary alcohol, you can only oxidize to one thing, and that is a ketone. And then you can reduce the ketone back down to the primary or secondary alcohol. And what we've seen for our reduction reagents is we can use lithium aluminum hydride or sodium borohydride. Those are our two main reducing reagents. Now I do want to go back and talk a little bit about the Rainy nickel, because that was sort of in the video, but I want to make sure we've talked about it. So these are the oxidation and reduction schemes for primary and for secondary alcohols. So in terms of oxidation, whenever you oxidize a primary alcohol, typically what happens is that if you use a strong oxidizer, it'll go all the way to the carboxylic acid. And it doesn't stop at aldehyde. It still goes from primary to aldehyde to carboxylic acid, but you can't stop. That's if you use a strong oxidizer. So what are our strong oxidizing reagents? Our strong oxidizing reagents are usually things that have metals in them. So potassium permanganate would be a strong oxidizer. Chromium trioxide and H2SO4 is called the Jones. That's called the Jones reagent. And so it uses chromium trioxide. You can also use potassium dichromate, K2Cr2O7. And depending, if you're starting with an aldehyde, things like oxygen gas can be oxidizers to oxidize an aldehyde to a carboxylic acid. And we have to be careful when we take aldehydes off the shelf because if they've been there a while and been exposed to a lot of oxygen, you'll have both carboxylic acid and aldehyde in your bottle. So these would be the primary strong oxidizers. And so you're looking in some of these cases at a chromium 6 plus oxidizer. Now the problem with these chromium 6 plus oxidizers is that they're a little bit toxic, and they're not environmentally friendly. If you've ever seen the movie Aaron Brockovich, and it's very dated, but it's like one of those movies they always show about environmental problems, and it's a movie about lawyers. It's not really a movie about environmental problems. But their environmental problem was the chromium 6 was getting into the water in the aquifer because they were storing it improperly, and they were using it to keep pipes from corroding and keeping the pipes clear. So chromium 6 is bad. Chromium 6 turns out to be an orange color, and chromium 3 plus is a green color. And what was funny in that movie was they always showed the green solution, they never showed the orange one. So whatever had happened had already happened. And this orange to green conversion could be used as a qualitative test for anything that can be oxidized. So you could take your primary alcohol or your secondary alcohol, add a couple drops of chromic acid to it, and the orange color would turn green, and that would tell you that whatever you had is oxidized by that. And we had to do that back in the day if we wanted to figure out what type of alcohol we had. Now notice tertiary alcohols don't show up here. And that's because if you have a tertiary alcohol with 3 alkyl groups attached to your OH, any kind of oxidation is going to be what we call a no reaction. You can't oxidize a tertiary alcohol because if you did, you'd end up with 5 bonds to the carbon. So only primaries and secondaries can be oxidized. And so these strong oxidizers will always take a secondary alcohol to a ketone. So the strong oxidizers will always do that, and they will always take a primary alcohol to a carboxylic acid. And so that's what those reagents do. We don't talk about any of the mechanisms for these because they're all kind of inorganic mechanisms. What you do see is the potassium permanganate is reduced. That's what oxidizers happen. An oxidizer is reduced. It always gets reduced down to manganese dioxide. You'll see that in lab when we do our synthesis of benzocaine, which will start next week. When we do that synthesis, we will take KMNO4 and react it, and we'll look for the disappearance of the purple color and the appearance of the brown precipitate, which is MnO2. The rest of the color changes you see. The problem is, what if you wanted to stop at the aldehyde? What if I just wanted to go from primary alcohol to aldehyde? And there's actually a number of reagents that will do that. And they've been developed through the years sort of as, some of them are more environmentally friendly reagents, but there's 3 of them that we use or talk about. So if you want to take a primary alcohol and convert it to an aldehyde, the first reagent that was developed was to use what's called it's chromium trioxide mixed with pyridine and another reagent. So this is called There's a version called PDC, and so that reagent will stop at the aldehyde. The pyridine basically kind of poisons the oxidizing capability of the chromium trioxide. So the problem with this reagent, the problem with all the chromium reagents are, this one has a double whammy, the chromium 6, and then pyridine is a little bit. Pyridine is a reproductive hazard, and so we don't use pyridine that much in the lab. So we got two problems with that. Then another one is called the Swern reagent. And for all of these, you would just have to give the name. You wouldn't have to give the reagent. Although on the final exam, you might see the reagent given. But what I do is I then go back and put the abbreviation there and say, this reagent equals that. So Swern is more environmentally friendly. And it involves using dimethyl sulfoxide and other reagents. And then there's also the Des-Martin periodate, which is sometimes abbreviated DMP. And so it also is a little more environmentally friendly. It uses basically what's called a hypervalent iodide. It works really well. A student a few years ago had to use it to make an aldehyde, and outside for the fact that it kind of built up pressure when she was shaking it, it worked great. So these two are more environmentally friendly reagents, but in the old days, the chromium 6 pyridine is what was used. So if you want to stop at the aldehyde, that's what these three reagents will do. Now, they will also take a secondary alcohol and convert it to a ketone. So they can be used either to form an aldehyde or to form a ketone from a secondary alcohol. Sorry. This reagent, chromium trioxide, pyridine, and HCl, is what's called PCC, pyridinium chlorochromate. And then there's also pyridine dichromate, which is PDC. But the one that's most common is PCC. These reagents should come to me like this, and for some reason that one didn't. I don't know if I should be concerned about that or not. It is Monday, so we'll blame it on that. So PCC, Swern, Des-Martin. The primary function of those reagents is primary alcohol, aldehyde, but they will take a secondary alcohol to a ketone, as well as all the strong reagents. Okay. So that's our oxidation scheme. Now, as far as the reduction scheme goes, of taking a ketone or an aldehyde down to their respective secondary alcohols and then our primary alcohols, we can't always use lithium aluminum hydride and sodium borohydride. They will always work. However, there is a hydrogen reagent that will also work. Now, one of the things we have to remember is that a carbon-oxygen bond is far more stable than a carbon-carbon bond. Okay? That's why when we were adding nucleophiles to the carbonyl group, it always, first instinct was, let's reform the carbonyl group, because the carbonyl group is very stable. And So if I just try to use hydrogen gas with palladium or platinum, I would not get these products. I would get a no reaction. So palladium and platinum is strong enough to reduce a carbon-carbon double bond, but it's not strong enough to reduce a carbon-oxygen double bond. And so a reagent has been developed called rainy nickel that when you combine rainy nickel as the metal catalyst with hydrogen gas, the rainy nickel will reduce the carbonyl. So whatever the carbonyl group is, you'll add hydrogen across that double bond and reduce it down to the alcohol. And it's really only going to work with secondaries and primary alcohol, or secondary with ketones and aldehydes to make secondary and primary alcohols. But you can do it if you use rainy nickel. Rainy nickel is a very porous nickel metal catalyst, and so what it does is it allows the hydrogen to absorb very nicely onto its surface, and then it can reduce, whereas just a regular palladium or platinum catalyst won't. And the reason, the importance of this kind of reduction scheme is, let's say for the sake of argument that you had a molecule that looked like this. We've got two functional groups. And so far we really haven't done a lot with multiple functional groups. Right? I mean, this year we're going to take them one at a time, and maybe towards the end we'll talk about how do you make a molecule with two functional groups, or what happens if there are multiple functional groups. Just realize that in real life, nobody's ever dealing with just one functional group. So if they try and react that one functional group, they got to make sure the other ones don't react. And so then we develop things like blocking groups and masking groups and other things to stop that from happening. But here's an example. Well, if I choose my reagents properly, I can reduce the aldehyde without touching the double bond. The double bond, well, for the moment, the double bond and the aldehyde are going to have to go together. And so let's try each of the three reagents. So if I reacted this with hydrogen gas and palladium and platinum, or I could react it with sodium borohydride, then H plus H2O, or I could react this with hydrogen and rainy nickel. So what would I get for each one of those combinations? Jacob?
For the palladium and platinum, would reduce the double bond,
but not the ketone. So I would reduce the double bond without touching the carbonyl if I just use hydrogen with palladium or platinum as a catalyst. What about the other two?
The rainy nickel, you'd use the same product from H2 platinum,
So I'm going to reduce both. If I used rainy nickel, I would reduce both, because if the rainy nickel is more powerful than the hydrogen and the palladium, then it'll also reduce a double bond. So if I wanted to reduce both, use hydrogen and rainy nickel. Now, the trickier one here with the H minus is, so sodium borohydride is hydride. Will hydride react with a double bond? A carbon-carbon double bond? No, why not? You know?
Or they both like have, they both have a lot. I don't know.
No, you were right. You were right. You're right in both cases. So, H minus nucleophile, carbon-carbon double bond, also a nucleophile. And remember, two nucleophiles won't react. So, the H minus is going to go after this carbonyl. It's the beauty of the carbonyl, right? Carbon-carbon dot bond, it's electron rich, there's no delta positive. Carbon-oxygen double bond, carbon's delta positive, there's my electrophilic center. So that's going to reduce, the double bond is going to stay the same, and I'm going to reduce that aldehyde down to a primary alcohol. So in terms of our reduction scheme, with these three reagents, we can pick and choose the reagent that we want. Now, you'd say, well, what happens if I want the double bond reduced, but I don't want to, well, we already know that. Double bond reduced without the aldehyde. What if I want to reduce the aldehyde without the double bond? Okay, I got that one. And then I can reduce both. So I can capture all three of these. Jacob?
Now, what if you want to reduce, or not reduce the double bond, but have the alcohol in a different place?
The alcohol in a different place.
Oh, never mind.
So if we wanted alcohol in a different place, well, then we'd have to react this with something. Like maybe you wanted the alcohol here. We would probably we'd probably use sulfuric acid to make the double bond here. And then we could add H plus OH, so we could add H plus H2O to put the OH there. But we're going to get to that by the end of the week. We're going to talk about what happens when you've got double bond, single bond, and double bond, because that's what's called a conjugated system. And that's going to be one of the products of the reaction. There's going to be a second one that right now you couldn't predict. Okay. So that's kind of our oxidation and reduction. I didn't talk about it in class when we went over it. I held off on putting that on the exam, not so much on the next exam. So it could show up there. Okay. So the other thing I want to talk about is the ethers. So we talked about ethers from the standpoint of how we make them by Williamson ether synthesis. But I probably should have gone back and talked a little bit about the physical properties of ethers, although there aren't very many. Because typically what we do with ethers is we use ethers as solvents. And the reason we use ethers as solvents is because they're very unreactive. Although the reactions they undergo are pretty spectacular, which I'll talk about in a minute. So when we do a Grignard reaction, we have to have a polar solvent that will dissolve the R minus MgBr. And the same thing would be true for, same thing is sort of true for an organolithium compound. When you look at those and say, well, they're ionic. So you need a polar solvent in order to make them dissolve. They're not really ionic. We'll just leave it at that. The Grignard is more ionic than the organolithium. Organolithiums will dissolve in hexane and benzene. It'll dissolve in hydrocarbon solvents. But the Grignard will not. So when I make a Grignard or when I do my Grignard reaction, I'm normally doing it in things like diethyl ether. The diethyl ether like we used in lab for extractions. So ethers are primarily used as solvents simply because they don't react with acids and bases. and they really don't react with nucleophiles or electrophiles. So they make great solvents. Because they don't have hydrogen bonding, they have low boiling points. So we can rotary evaporate them and remove them from the reaction mixture. And they're nonpolar enough that we can do extractions. So ethers are ideal solvents. And that's what we found in lab last semester because we were using ethers to do extractions. The only problem with them in terms of physical properties are that, number one, they're extremely flammable. So, I mean, diethyl ether was used as to knock people out for surgeries initially. They found that it had that property, but then you had to be careful that you didn't have any sparks or, anything like that, or else, you had a fire or explosion hazard. Same thing's true for ether when we're in the lab. That's why we don't mess with ether with flames, and we don't use ether. We try not to. We don't use it directly on top of a hot plate. We always have that water bath because it will catch on fire. And the other thing it will do is, because the ether vapors are heavier than air, they will sit on the bench top, so that if somebody's extracting something with ether over there and somebody has a flame here, they can set the vapor on fire, and it makes this whoosh sound as the flame moves across the bench. I heard that once in graduate school. And then I looked, and the guy in the lab was like, can you get the fire extinguisher? And I looked, and all I saw was the orange backlighting on the wall. And then I had to go over and tell him to move because he had backed up on and was basically sitting on the fire extinguisher, and then we put it out. And then we handed him the fire extinguisher and said, good luck with the paperwork on this one. Because what did he do? He was trying to recrystallize something by putting the beaker directly on the hot plate. So I think he then went and got a water bath and claimed that he had done it the proper way. This is why I have these, we all have these little pet peeves in lab, and that's why I stress whenever we're using ethanol, methanol, or ether that we always use a hot water bath. Because then I'm dragged back to my experiences of putting out the fire. And the post experience of going, yeah, no, that's not really what happened. So it's extremely flammable. So we have to be careful. Some people will use an ether called like tertiary methyl ether instead. They'll use that in the lab instead of diethyl ether. It's less flammable. It's got a higher boiling point, but I think it's got a very disagreeable smell. And the T-butyl methyl ether, which is called TBME, this was a gasoline additive. They didn't always put ethanol in your gasoline for your winter mix. When they say they have it has a certain amount of ether or a certain amount of alcohol in your gasoline. They use this, and there's probably a ton of land that has this in it because the gas station tanks leaked, and it had this compound. So I don't think it's in favor anymore. I think you just use the alcohol if you want to add an oxygenate to your car. That's one issue. The other issue is the formation of peroxides with ethers. And so when we're talking about peroxides, what we're talking about is putting an oxygen-oxygen bond. So here's what happens with diethyl ether, and this is going to kind of foreshadow some things that we do later in the week when we start talking about free radicals. because this is a free radical mechanism. So if diethyl ether is allowed to sit out, well, first of all, if it's just allowed to sit out with no cap, it evaporates, which causes it catch on fire if it comes near anything. But when you have bottles of ether that just sit around for year after year after year, what can happen is they can react with oxygen gas. Now, oxygen has a paramagnetic form where it has unpaired electrons. And if you've ever seen a video where they take liquefied oxygen and they pour it through like the poles of a magnet, you can see the stream of liquid oxygen being attracted to the magnet. That shows that there is a paramagnetic form of oxygen. So it is a source of radicals. A radical is something with an unpaired electron. And by definition, radicals are very reactive, both in the chemical sense and in the real life sense. Right? So if you're a radical, you're very active in whatever you're going to do. This is reactive because it doesn't have paired up electrons. So whenever we breathe in oxygen, we're breathing in free radicals, basically. And we'll talk about what happens later, how our system kind of neutralizes those. But in this case, what happens is that that oxygen will react with one of the hydrogens that's attached to the carbon next to the oxygen. So I'm using fish hooks here to indicate the movement of one electron. So if you can imagine this carbon-hydrogen bond breaking, and then that H dot combining with this O dot, what we end up doing is we end up forming that carbon with an unpaired electron, and then our oxygen gas has pulled off, or what we're going to call later in the week, abstracted a hydrogen. So it forms that radical. Now that radical actually would be stable because you could imagine maybe I could write some resonance structures for that. And so it wants to remove the hydrogen next to the oxygen. Then what happens is the radical, this is now called the peroxy radical, will then come in and it will couple directly with that carbon radical. Okay, and the term that we use whenever two radicals come together to share electrons is coupling. That's the term that we use. So we're going to have this coupling reaction where the O dot combines with the C dot to then make that molecule. And so this is called an organic peroxide. Hydrogen peroxide is HOOH. An organic peroxide is either ROH or ROOR. We saw that last semester when we talked about anti-Markovnikov addition of HBr. That's when we used ROOR. So this is an ether peroxide that I just made. And Explosives 101 is that if you want to make a molecule that will have the biggest bang, what you do is you make it a solid that goes into a gas, because that's your biggest expansion of volume, and you embed a gas molecule into that molecule you want to make explode. Okay, again, don't do this at home or in the dorms or in the labs unless you have somebody else for lab to do the paperwork. But that's how we make things explode. That's how we make explosives. is we embed gas molecules into it. Sometimes it'll be a nitrogen-nitrogen bond. Sometimes it'll be NO2, a nitro group. All of these will form gas molecules. So what happens is that as the ether sits around for years, it forms these peroxides, which are solids that then fall into the bottom of the container. So it used to be that if you walked up to a bottle of ether that was sitting in a shelf and you looked at it and it was in a glass bottle, number one, don't touch it. Because glass bottles are even worse. And now what they do is they add inhibitors to ours. We don't have glass bottle ethers. We only have ones in metal containers. But in the old days, people would say, oh, there's an ether bottle. It has solid at the bottom. It's like, don't even be in the room with it. And then you have to call the guys out. They come out in like spacesuits to get rid of it. I have seen them walk across the parking lot. And I don't know why they just didn't put it in a bomb detonation thing, as they took it somewhere to basically explode it. Because bottle had been sitting in a lab for years, like 10 years. So we have to be careful with ethers. If you try and rotary evaporate an ether with peroxide, sometimes it will explode the round bottom. Again, another thing I'm constantly, make sure when you get near the rotovapes, make sure you've got your goggles on, because I think this happened. I think it was a peroxide that caused a round bottom to explode in the lab across from me. The chunk hit the person in their safety glasses, so they had like industrial safety glasses. It hit and took a chunk out of the safety glass. It would have taken much more had the safety glasses not have been there. And I think it was because the ether had a little bit of peroxide in it. So we have test strips, we can test it, and then usually we'll add a little iron to it to kill whatever peroxides are there. But we have to be very careful when we use ethers because of this formation of the peroxide. We haven't had any of those situations that I know of for a while. I did get a panicked call one day from a high school teacher at Riverside. Right, that's the one that's in Painesville Mentor, right? It was one of our former students. He said, we have a bottle of diisopropyl ether sitting on the top of their workspace. And I said, well, why? I said, you're not in the same room with it, are you? And he's like, I said, get out of the room. Because it's old and I'm sure it has peroxides in it. And the reason I suspected that is because with diethyl ether, you basically only have a primary carbon that you're forming the radical out of. If you have a secondary radical that you're forming, it's going to form even faster. And so there was no question that there was peroxide in that one. And I said, well, you need to call somebody because that's not a good situation. So apparently another teacher that did not last long at that high school, I don't believe, went in and just took care of it. And I said, well, give him this advice. If he's going to pick it up, tell him to pick it up with the hand that he doesn't write with. Which is actually rule number one. If you think anything's going to explode, always pick it up with the hand you don't write with. So at least you can write if it blows off digits or hands. I've never seen that happen, but this one I was just like, just leave it alone. But he decided not to leave it alone. He didn't lose anything, fortunately. So we have to be really careful with these molecules. That's the big two things about ethers. We love them as solvents, but they are flammable, and they do form peroxides over time. And so we have to be very careful of that. Okay. Another thing about ethers is we talked about how to make them. So we made them by basically taking our alcohol, converting it to an alkoxide, and then reacting it with a primary or secondary alkyl halide, chloride or bromide. And we can react our alcohol with either an H minus, a C minus, an N minus, which is in reverse. Normally we'd say N minus, C minus, and C minus and H minus are equivalent in terms of basicity. So we can make an alkoxide by direct deprotonation. N minus, C minus, H minus. Or we can also make them with sodium or potassium metal. And I don't remember in this class if I talked about the sodium or the potassium metal, but I'm trying to get myself in the same place with both classes. So when you react an alcohol with sodium, you end up with the alkoxide and hydrogen gas. And I would just remind you that in general chemistry that you ended up doing the same reaction, except it was a lot more reactive. So if you added H2O to sodium, you made sodium hydroxide and hydrogen gas. If you react an alcohol with sodium or potassium metal, you make the alkoxide and hydrogen gas. So if you've ever seen the reaction of water and sodium, I don't think anybody does it in general chemistry. Maybe Dr. Challen does. That's usually at least once a year some high school teacher does this, and it basically like blows stuff up through the first 2 rows of the class, and then it makes national news, and they have to, and then it's like, don't do that demonstration. There's plenty of YouTube videos. But this reaction, it's the hydrogen gas, it'll spark, and if you have hydrogen gas, then the spark catches the hydrogen gas on fire, and that's what either causes it to shoot up or blow up the container that you're in. Alcohol would be even worse, except it's less reactive, because your alcohol could be flammable as well. So when we do these reactions, we usually do them with very small pieces of sodium metal in an inert atmosphere, so at least we don't have the oxygen to sort of combine to help the oxidation reaction along. And I don't think there's any, on YouTube, if you just look up sodium and hydrogen, you can see the spectacular reactions. My favorite was they took a piece of sodium metal and they made like a little boat out of it. They pounded it out and like folded it up. And then they got some Hot Wheels track. If you know what Hot Wheels track is, this was a toy from my childhood where you could like take the Hot Wheels and like loop-de-loop and shoot them halfway across the yard. But they took the Hot Wheels track and they let the boat slide down into a kid's kiddie pool. And then it floated for a second and then it exploded. I've heard of worse things, but I won't tell you about that. So that's kind of, it's the exact reaction of water with sodium is the same as ROH with sodium. So when I usually say HOH, ROH, react the same, this is another one of those examples. So we make our alkoxide. Then once I have the alkoxide, I can react with a primary or secondary alcohol, and I can now form, in this case, what I would do is I would add the isopropyl group to that. And remember, that one's called the Williamson ether synthesis. And with the tertiary alkyl halide, it does E2. So that's one of the ways that we could talk about, that we could make ethers. But there's a whole series of alcohol reactions that we can use to make ethers that I'm going to put in the classification of review, because the mechanisms kind of make sense. So if I gave you a reaction of methanol and isopropanol and I said, let's use an acid catalyst, and we could make methyl isopropyl ether. Now, this acid catalyst would most likely have to be sulfuric acid. There's two mechanisms for this reaction. Tell me what I should do. First step in the mechanism.
Protonate the oxygen.
Which one? You're correct. Protonate the oxygen, but which one do you want to protonate? And it doesn't matter because there's two different mechanisms depending on what I choose here.
CH3 always.
Okay, let's protonate that one. Okay, so let's protonate the CH3 OH, so I'm going to form an oxonium ion. Okay. So, can the water leave? No. So what's going to happen in the next step then? Remember, my ultimate goal is to make this ether. We need a hint. If the water left, I would do an SN1 mechanism. Since the water can't leave, what mechanism am I stuck with? Take a guess. SN2. So for my SN2 mechanism, what I'm going to do is I'm going to take my isopropyl alcohol and I'm going to have it come in and attack the methyl group and kick off the water. And so what am I going to end up with? I'm going to end up with that oxonium ion. And so this is an SN2 mechanism. And then what's my last step then in the mechanism? Lose the H plus to then form the final product. So the reason I would call this review is because it's an SN2 mechanism. I also seem to recall last semester, for those who were here taking organic last semester of any kind, that we had this mechanism as a side reaction when we took our butanol and made butyl bromide out of it. This was how we could form dibutyl ether. Okay. But if I protonate the oxygen on a carbon that will not form a carbocation, I got to do an SN2 mechanism. Okay. So, take home quiz. Should be really easy. Maybe. I want you to protonate the isopropyl alcohol first. Do the SN1 mechanism that will end up giving me the same product. Sure. And since it's SN1, you don't have to worry about the the trigonal bipyramidal SN2 transition state. But start by protonating the isopropyl alcohol and then have the methanol react with whatever that turns into via SN1. And our final reaction of ethers that we need to talk about is what's called ether cleavage. So then what I would like you to do, also as part of your take-home quiz, is I would like you to react this ether with 2 equivalents of HCl so that the 2 products I get are isopropyl chloride and methyl chloride. And there's 2 different ways to do that. I just want to see one. Okay. So it could that mechanism could be a combination of SN1 and SN2, but that's what we're dealing with. So I'm reacting with H plus Cl. What's the first step? Protonate the ether oxidase. So I would like you to do those 2 as a take-home quiz for Wednesday. And then we'll finish up this ethers, and then I'll change the reading assignment. If you want to read ahead, we're going to start with free radical halogenation on Wednesday and probably finish that. Well, we definitely will continue with that on to Friday. I'll put the deadline for Chapter 15 online. It'll probably be due at the earliest Friday. So if you haven't started on those problems, you might want to now. But I'll get everything squared away for Wednesday.